All right, one very simple example. You have a block, and it says block sliding to rest on a bumpy surface. So you have a block, and let's say, I'm just going to say it's got some velocity v naught. They don't tell you what it is, and it's moving. So the best habit I can get you into, I know for forces, we said do your 5 steps for success, draw a picture, label your forces, pick your coordinate system, sum your forces, and solve. And I did that really quickly. But you have your 5 steps for success. Well, if I can hit home any big physics thing, if you draw a picture and you're like, okay, I'm gonna draw a picture of what's going on here, and I have some block sliding to the right. And velocity is not a force, so I did not label that on my FBD. I just said this block is sliding to the right here. And if they said make an FBD, you could sure label gravity, normal force, and whatever forces are acting on it. But they just said some block sliding to the right. And as soon as I know it's moving, I've identified the energies that are going on. It has kinetic energy. Now, one little thing, energy is a scalar, so I don't need to put a coordinate system in here. I know that's weird, but if you're going to use the tools of energy, you do not need to put a coordinate system in here. If you're going to use forces, you should put a coordinate system in here. And I picture, in physics, I'm giving you tools, kinematics tools, forces tools, energy tools. And a lot of times, and on the next example, I'm going to show you can use forces and kinematics to solve a question. But another tool that you have available now, you're going to have available to you is the energy tool. Okay, so you go to your toolbox, you're like, hey, what tool do I think is going to get the job done most efficiently? So let's just talk through the energy tool right now. This block is sliding to the right. As soon as I know it's moving, it's got some type of kinetic energy. I'm just picking nice numbers. Again, I said 10 joules. I do know that it has 0 joules of potential energy because it's on the ground. The height here I'm going to call 0 meters. And if you look back, your kinetic energy formula is 1/2 mv squared. Your potential energy formula is mgh. So if you ever have a block or something that's on a height of 0, like it's on the level ground, it has 0 joules of potential energy because it's not lifted in the air at all. Gravity is not going to do work to bring it down farther. It's at a height of 0. Okay, so identify it's got some joules of energy. I just made up a number, 10 joules. It's got kinetic energy, that. It's got PE, that. And then it hits this rough patch. And I did purple dots. I use lots of colors today. And eventually at the end of this friction-y kind of surface here, it comes to rest. And you're like, whoa, I had kinetic energy 10 joules, and at the end, it comes to rest, so it has 0 joules of kinetic, and it still has 0 joules of potential because it didn't rise or fall. So you're like, whoa, energy, this must not have been a conservative force because energy was removed from our system, right? If you take your KE plus your PE, 0 plus 0, that equals 0. It's not 10 plus 0, which was 10, so the energy went somewhere. That just means that 10 joules left our system because of work. And it could be the work done by friction, which caused it to leave in the terms of heat, but we can account for that. So I just wanted to highlight that, is that, yeah, we talked about on the roller coaster example there how energy could be transformed as heat, but friction did the work to remove it from our system. And it's not like you violated the conservation of energy. You take 0 plus 0 plus the 10 joules lost because of friction, it still adds up to 10. It's just that it's not a conservative force, because to be a conservative force, when you add KE plus PE, it should remain constant throughout. Okay? A non-conservative force, you transform the energy into heat, maybe due to friction, and you have to account for that. Okay? So we're going to start simple. We're going to go back to a classic, and I will say this by now should be like, okay, I can do this. So, big example. We're going to do it using the old school techniques of forces and kinematics, and then we're going to do it using energy, and you're going to see energy ways quite a bit easier. So you're going to draw a block on a ramp, and here's what you know about your ramp. You're given that it's starting at a height h, and the length that it's going to slide down is delta x, right like that, from the center of the block to the very end right here. And maybe that'll be when the center gets there, but don't get hung up on that. And let's say that ramp has an angle of theta. So, and I know we're in the energy unit, but we can't let our old tools go to waste. So we're going to review our forces example. So given this, you want, what's the final velocity as the block gets to the end of the ramp? Okay? And as soon as I hear things like final velocity, I think, yeah, I eventually am going to have to use kinematics. And if I need to use kinematics, you got to ask yourself, how do I go from forces to kinematics? And if you remember one thing from forces, if you can find acceleration, acceleration is your link back to kinematics land. Okay, so step 1, we drew our picture. Step 2, I'm going to label my forces. The force of gravity, because we're on planet Earth, goes straight down from the center of mass of the object. And since that block is touching the ramp, you have a normal force, whoosh, just like this, Fn. And I'm going to say there's no friction in our ramp because I just don't feel like getting really complicated today. So I'm going to say my FBD is done. I have force gravity going straight down. That's going to form the hypotenuse of my triangle right there. I have force normal because of Newton's third law. For every action, there's an equal and opposite reaction. The ramp is pushing back up on the block. And then step 3, I'm going to choose my coordinate system. Now remember, Forces and kinematics are a little bit more of a pain just because they're vectors, so you have to include the direction and the coordinate system like that. That's why energy is going to be an easier tool for this type of question. So I did all the first 3 steps. Picture forces, coordinate system. I tilted my coordinate system so it lines up x-axis with the ramp right there. And then I have to sum my forces. So hit pause in the video, see if you can still sum your forces in the x direction. And I'm going to give you a hint. You have to break the force gravity hypotenuse here, boom, into like the y part and the x part. So hit pause, see if you can do that, okay? All right, we're back. And I'm going to do this very quickly. But when you break this up, this force gravity has an adjacent component right here. Boom. And it has this opposite component right here. Boom. And remember, that theta right there is the same as this theta right here. Just like that. So I'm going to sum my forces in the x. And when you do this, I say force, gravity, and the x. Now, one little thing. Remember, fug equals mug. So I'm like, oh, this hypotenuse right here, this force gravity is mg. But in the x direction, I don't get all of that vector. Remember, if you give you the hypotenuse, you have to break into x and y components. So I say, I get, fug equals mug. I get the mg right here. Mg, which is the overall weight of the block, but I don't get all of it. That's all of it right there. I don't get all of that in the x direction. I get the opposite component, this part right here. So I say, of that weight, I times it by the sign, because that's literally just picking out the opposite component right here. And you can draw the triangle like we've done before and prove it to yourself. Newton said the second law is F equals m times a. And, you know, it's accelerating down the ramp, so you get mg sine of theta equals max. You have m's on both sides. They cancel. So you find out that the acceleration of this block down the ramp is g sine of theta. Super important. It's mass independent, okay? So you could have a big block, a little block, massive block, light block, whatever. Your acceleration is independent of mass. And you're like, okay, once I have the A, I can link back to kinematics. And you're like, you know what? They gave me the delta x. They said, oh, let's say the initial velocity was 0. It starts from rest. And you know A now? Well, you can solve for the final velocity. So you take your acceleration, you run it through the equation like we're doing, and you'll get something like this. And I'm sorry if I didn't tell you the initial velocity was 0. I'm just going to say it starts from rest. And you're like, okay, good. And then you have this right here, and for acceleration, I plug in g sine of theta, and I say, that is my final velocity at the bottom of the ramp there, after it's slid down the ramp a distance of delta x to the bottom of the ramp right there. And keep in mind, when you're squaring stuff, yes, it was moving in the positive velocity direction, so this would be a positive velocity. But keep in mind, when you're squaring stuff, you do lose information about the sign. That took a couple steps. I sum my forces in the y, even though there's no friction, because I just like to solve for normal force. Just out of habit, it's just good. I will say we did not need that to solve this question. The big thing is we used forces to get acceleration. Then we went to kinematics lines right there. Okay? Now, that took about 2/3 of a page, maybe even 3/4 of a page. Let's do it using the energy way. Once again, I'm going to draw the ramp. And this is an H. That's a bad H. Just like that. So we're going to draw the ramp. And if you didn't get the forces way, you got to hit pause and you got to make sure you can do it that way. But the energy way is going to be quite a bit nicer. Now, here's the cool thing. If you're going to use energy to solve this, you don't need to draw a free body diagram because that's for forces, right? So that's kind of nice. You don't need a XY coordinate axis right there because energy is a scalar. So right off the bat, and this is the theta, it's just not a good theta. And they're going to say it slides down a distance delta x just like this. Boom. That's a bad x. All the way down to the bottom right here. Yeah, my drawing's going downhill. And let's just say the block has mass m. They didn't tell us much about the block. I didn't even need that up there because the m's cancel. That's kind of cool. If they ever don't give you the mass, it's probably a pretty good indication that it's going to cancel. And once again, they're going to say, hey, find the final velocity at the bottom of the ramp. And the only thing that I'm going to emphasize more in this one, I said it started at a height h before, but I never even really used that. So just keep that in mind that we're going to have to relate h, delta x, and theta. So maybe actually we'll do that right now. I'm just going to put this little note here. The sine of theta equals the opposite over the hypotenuse. So in this case, it would be h over delta x. Let's just write that there because that's the only thing that we might have to come back and use at the very end. And I know we're going to have to use it just because I've taught physics for a while. All right, so we do this. Now, when you're doing energy, the first step you should do is say, is there any outside force acting on my system besides, say, gravity, right? And since they said there is no friction, and there's no other person pushing the block or pulling the block or doing whatever, you'd say the only force acting on the system is gravity. And if that's the case, energy will be conserved because gravity is a conservative force. So you can say E final minus E initial equals 0. You're just going to use the conservation of energy. Step 1, when you're doing an energy question, ask yourself, are there any outside forces that are acting on my system? Because if somebody's pushing that block or pulling on it, that's an outside force. We got to account for it. But if it's the case that it's just gravity acting on it, then you just start with your very simple definition, E final minus E initial equals 0. This is the conservation of energy, and it's a really, really big deal. I know it sounds crazy, but let's say you're doing a question like this, and you even write down E final minus E initial equals 0 because you identified there's no outside forces acting on it besides gravity's acting on your system. They'll give you a point for that, just because they say that person knows the conservation of energy. If there were an outside force, we have to do one little thing that's different. We have to set it equal to work, and we're not going to worry about that today. Okay, so E final minus E initial. Now, super important, you have to identify what energy type do I have at the beginning. Well, this block is raised up the ramp and it's just hanging out there. You have potential energy at the beginning, okay? And you might be like, well, do I also have kinetic energy? And your gut would say, well, is it moving? And they say it's not moving. So if it's just raised up in the air, I always picture like it has potential to fall, it has potential energy. And if it were moving, it also have kinetic, but this block is just hanging out stationary up in the air, okay? Just like you raised a rock up in the air and you're getting ready to drop it, has potential to fall, it has not done that yet, okay? The block goes down the ramp, and halfway it might have PE and KE, right? And then as it falls more and more down the ramp, the height is decreasing, so its potential energy is going down, and it's kind of like PE is going down and KE is increasing. At the very bottom, it reaches its max speed, because you know at the bottom here, it's got a height of 0 meters. So going back to what we said, potential energy is mgh. If you have no height, that means you have no potential energy. And all of that PE is transformed over to KE. So the block is going the fastest at the very bottom because all of its PE has transformed into KE. Okay? They love questions like that, like where are you going the fastest on the ride? Well, you got to find out where your potential energy is the minimum value, because that's where you have the maximum value of kinetic energy. I picture like a gas gauge. As one goes up, the other goes down, but the sum remains the same. Okay? So, all right, step one, you're using conservation of energy appropriately. You set it equal to 0 joules because there's no outside force acting on it. We just have gravity acting on our system. And you say, my final energy was kinetic energy. And I know the formula for kinetic energy. It's 1/2 mv squared. So it's really important to identify what energies are present at the end and what did you start with at the beginning. And you say minus my initial energy, which was potential energy, and the formula for potential energy is mgh. Okay? And one little thing, you might want to get the height in terms of the variables they actually gave you in the question. So we said, oh, height in terms of what they gave us. The height, I'm just going to do it, will be equal to, I'm just going to times delta x over delta x sine of theta. In terms, and that's just because that's in terms of the letters they gave us there, delta x and theta, so I can get them speaking the same language as the first part of the forces example. So you're like, okay, I identified the conservation of energy. Then I identified what energies I had at the beginning of my problem and at the end of my problem. And then I'm just going to plug those into my formula, 1/2 mv squared minus mgh. And you're going to solve for v final. So one little thing I just did in my algebra step, I just added that over, and I'm going to cancel m's on both sides then, and I'm going to solve for v final. And when you do it, you get v final equals the square root of 2gh. You're like, whoa, whoa, whoa. Square root of 2gh, that's different than we got using the forces and kinematics way. But here's the sweet thing. The only reason it looks different is because I put my final answer in terms of delta x and the sine of theta. And keep in mind is that we know the height of the ramp in terms of delta x and sine is delta x times the sine of theta. So when you make that little substitution that h is delta x times the sine, you get your final velocity as square root of 2g delta x sine of theta, square root of 2g delta x sine of theta, just a little different order there. But it's the same answer. And I just rearranged it at the end so it was the exact same answer. But the cool thing is, when you do it the forces and kinematics way, you gotta go to force line, get the acceleration, then you take your acceleration, you go to kinematics line. It's like a couple of steps here, right? When you do it at the end, direction matters because forces and kinematics are vectors, right? When you use energy as a tool, your diagram, you don't need to make an FBD unless they wanted you to make an FBD and they said make an FBD. But you say, you identify your energy at the beginning, PE, which converts over to KE at the end, okay? All the PE goes to KE, and then you just work your equation right here. And you're actually just working the conservation of energy, okay? And yes, they can get more complicated, and yes, we will do that, but this is a great example to start with. All right, so I hope that helps. And if you only master one thing today, make sure you master the forces and kinematics way. And then if you master two things, try to do it the energy way and get it to work out the same, because that's why physics is so neat, because unit 1 we did kinematics, unit 2 we did forces, unit 3 we're doing energy, but they're all related. You're just making your toolbox of physics knowledge, and then you get to use it. All right, so I hope that helps.